Hi everyone, welcome to the Advanced Topics in Statistical Physics. This is Haotosaki. In this mini course, I'd like to discuss the absence of ferromagnetic order in the classical two-dimensional XY model. Okay, so this is the final slide of this lecture, but the main topics of this mini course is something called Wegener's harmonic approximation for the XY model, and also a beautiful theorem by McBride and Spencer about the absence of ferromagnetic order. Okay, anyway, so let me start. So this is part one, but I'd like to discuss carefully the background. Okay. So first of all, I'd like to discuss three standard classical spin systems. Okay, and this is a basic setting about lattice and the set of bonds. So first of all, D denotes the dimension. It could be 1, 2, 3, 4, or well, actually 3 is enough, but it can be anything. And we consider the D-dimensional hypercubic lattice, which is defined mathematically this way. Okay, when d equal 1, this is simply the set from 1 to L, and it's called chain. When d equal 2, this is called the square lattice, and for d equal 3, it's the cubic lattice. In general, we call it the hypercubic lattice. Okay, and the site, the element of lambda, the lattice is are called sites and denoted like UVW. And if you express this in coordinate, U in coordinate, it looks like this. So it has D components, and each component takes this integer value from 1 to L. I think this is clear. Okay, so now we define the set of bonds, and by a bond we mean an unordered pair of two sites. Okay, and actually in the final part I will consider ordered bonds, but in general in most places I just consider unordered bonds. So I use this notation as a set. U, V, and VU are the same thing. Okay, and so this is a set of bonds, and it's the set of pairs of sites, and I also require that U and V are nearest neighbors. Okay, and by nearest neighbor I mean that their distance is 1, or they are neighboring in the language of periodic boundary conditions. Okay, so here's the simple picture of square lattice with L equals 3, and this is a picture of corresponding bonds. So these two sites are neighbors, so this is bond, and this is also bond. But we take periodic boundary condition, and U and V satisfying this. So what is this? Well, these parts I regard as the same, and these parts are the same. And only these parts are different, and it's L here and it's 1 here. So it means that this one and this one are also neighbors. And I think most of you are familiar with this notion of periodic boundary condition. So this one and this one are also neighbors. Okay, so this is our set of bonds. I think this is clear, and I'm going to use this definition throughout this mini course. Okay. All right, so I will consider first of all the ferromagnetic Heisenberg model. Actually, we do not discuss this model in detail in this lecture, but anyway, this is the most standard. Okay, first of all, spin at site U is denoted like this, and this is nothing but a classical vector, three-component vector with size 1, length 1. Okay, and by a spin configuration, we mean this simply the collection of all these spins on all sites. Okay, all these things. And now here's the Hamiltonian, or the energy. Of course, it must be a function of spin configuration, and these are parameters: the system side and the external magnetic field. Okay, so it consists of two parts. First of all, we have sum over all bonds of this term, which is usually called the Heisenberg interaction, and it's simply the inner product of two neighboring spins. Okay, and so since this is the inner product and we have minus sign, okay, if you want to lower this energy, then you want to make this inner product large. It means that the two spins want to align in the same direction. So this is why we call this ferromagnetic model. And this one expresses the magnetic field in the x direction. Here you have the x component of this spin, and you have this combination. So if you want to lower this energy, you want this to be big. That means the spin is pointing in the positive x direction. Okay, so these are the configuration. This is the energy. Then you can do statistical mechanics. Okay, as usual, this denotes the inverse temperature, which is always positive, which is always strictly positive and less than infinity, finite. And this is the partition function. So you have e to the minus beta h, and simply you sum over all configuration. But in this case, since this takes continuous values, you cannot simply sum. So this ds integral means this. So this is simply the integration over a single spin over all possible values, all possible directions in 3 dimensions. So you just integrate with this condition, okay? And you want to do that for all sides in the lattice. Okay, so you take product. And this is a partition function, and similarly, you can define the expectation value of any function of spin. You put it here, and then you get this average. Okay, so this is my notation. It's a bit complicated, but I want to denote what the parameters are. So this is a system size, inverse temperature, and the external magnetic field. Okay. I think this is clear. So this is ferromagnetic Heisenberg model. What is the XY model? It's almost the same. I just copied and pasted. So now spin, in this case, has 2 components. Okay. So of course, dimension can be anything, but the spin is sort of 2 dimension. So we have, oh, here's a mistake. This is all squared. Okay, so spin has 2 components like this, and again, the size is fixed to be 1. The spin configuration is this, and Hamiltonian is exactly the same. Okay, now partition function is again the same, but now here I just integrate over all these spins. And this is the expectation value, again the same. And then we have the well-known Ising model. It's also called the Lentz. Probably we should call this the Lentz-Ising model. And now in this case, spin is no longer, well, you can regard this as a vector, but anyway, it only takes 2 values, 1 and minus 1. Okay, and this spin configuration is simply the collection of all these plus minus 1s, and this is Hamiltonian. So this is ferromagnetic interaction, and now magnetic field is pointing in the positive sigma direction, and this is a partition function. Now you simply sum over all possible spin configurations. There are 2 to the L to the D configuration. You simply sum over them, and then this is the expectation value. Okay, so let's discuss the physical meaning, physical characteristics of these 3 models. First of all, Heisenberg model, it's no doubt it's the most natural and realistic model of interacting spins. And because, you know, spin is basically a 3-dimensional object, so if you want to treat it classically, then the most natural treatment is that treat it as a 3-dimensional vector with a fixed size. And this interaction is simply the inner product. It's very natural and basically realistic. But I would say that antiferromagnets are more realistic, and you find more actual materials. But anyway, we are not discussing about this kind of actual magnetic systems. So anyway, so this is natural and realistic. Nobody would, I think everybody would agree that this is most natural and realistic model. And the Ising model, again, this is very important. And this is model of ferromagnets with strong axial, strong uniaxial anisotropy, whatever. So I mean, in actual material, you always have some anisotropy. So if you have, well, if you have some nice anisotropy, then you may model a magnet rather faithfully by using Ising model. But I think more importantly, the Ising model is the simplest model for studying collective behavior of interacting spins. So it has very important, it has very important meaning from you know, the basic study of statistical mechanics. Okay, so the XY model is sort of intermediate between them. And of course, you can again argue that this is a model of certain ferromagnetic system, but I don't think there are many realistic models of magnets which behaves like the XY model. But from theoretical point of view, I think this is important, very important. And as I will discuss, this XY model has a continuous symmetry, and the Ising model has a discrete symmetry. And the XY model can be regarded as the simplest theoretical model which have continuous symmetry, and this is very important. And actually, this continuous symmetry is the essential topic in this mini course. Okay, and also I'm not going into detail, but actually it turns out that this XY model is a rather nice effective model of superconductors and superfluids. And of course, these are quantum systems in which the quantum mechanical U1 phase plays an essential role. And in these systems, this U1 order parameter plays an essential role. And this is somewhat similar to the XY spin. And this makes the XY model a useful, effective model for these systems. Okay, so this is a side remark, but physically this is an important thing. Okay, this was just a brief remark. So let me discuss the symmetry question in detail. So suppose that the magnetic field is zero, okay? And I want to see what symmetries our models have. So first of all, let's consider the Ising model. So this is our Hamiltonian. Then it's clear that this Hamiltonian is invariant or the global spin flip, like this. So this minus sigma denotes the spin configuration where we take minus. Where we flip all spins. Okay, since we have this interaction, so if you put minus here, nothing changes, so we have this symmetry. Okay, so in this case, if you flip everything once and twice, then you return to the original. So this kind of symmetry is usually called Z2. You don't have to worry about this group theoretic language, but anyway, in this case, the model has discrete symmetry, which is Z2 symmetry. Now let's consider the xy and the Heisenberg model with this Hamiltonian. Again, we have h equals 0. And in this case, I argue that this is invariant. The Hamiltonian is invariant under the global spin rotation. Actually, this has more than global spin rotation, but anyway. So I claim that this Hamiltonian satisfies this invariance. What is this? Well, here R denotes an arbitrary orthogonal matrix, n by n orthogonal matrix, where n is 2 for the xy model and 3 for the Heisenberg model. So this is nothing but the number of components. Okay, and since the as you know, the orthogonal matrix does not change the inner product. So you see from this that Hamiltonian is invariant. Okay, so in this case, so the ON contains usual spin rotation, and you can rotate something in a continuous manner. You can change the angle continuously. So in this model, in this case, the model has continuous symmetry. This is very important, as I discussed. Okay, so now before discussing the XY model, I like to quickly review the ferromagnetic, how we can characterize the ferromagnetic order in the Ising model. So I mean, I discussed the characterization in terms of the spontaneous symmetry breaking or the long-range order. Okay, so when dimension is greater than or equal to 2, it is well known that this Ising model undergoes a phase transition at some critical point. Okay, and so this is inverse temperature. So this means that beta is larger than beta c. This means that the temperature is lower than the critical temperature, and we know that in this low temperature region, the model has ferromagnetic order. And there are two ways of characterizing ferromagnetic order. Number one is in terms of spontaneous symmetry breaking, SSB. Here we focus on something called the spontaneous magnetization, which is defined in this way. Okay, here this is the total magnetization divided by the number of spins. So this is the magnetization density evaluated at system size L, inverse temperature beta, and strictly positive magnetic field. And then you take the limit in which L goes to infinite, so the infinite volume limit, and then after that you let H go to 0. Okay, and then it is known that when beta is less than or equal to beta c, so if we are in high temperature region, this is 0. So this is reversibly known. And in this low temperature region, this spontaneous magnetization is strictly positive. Okay, here's one remark. We are using periodic boundary conditions. So this can be rewritten, can be simplified. First of all, note that because of the linearity of expectation value, you can write this in this way. And then, but you see that this expectation value is independent of u. So instead of simply summing over all and dividing things, you can just pick an arbitrary u, and these are the same. Okay, expectation values are the same. Of course, these quantities are different, fluctuations are different, but anyway, the expectation values are the same. So you can also define this spontaneous magnetization this way. You pick an arbitrary u, expectation value of sigma u, infinite value limit, and h goes to 0 limit. Okay. Now here's a very important observation. Suppose that h equals 0 and L is finite. And then because of this global spin flip symmetry, when h equals 0, the symmetry implies this expectation value of sigma is 0 for any beta and for any u. So this means that we have this. Well, what is this? Well, this is very similar to this, but look, there is a subtle difference. We have double limit, but here you first make h go to 0, and then by continuity, this is same as this, or this is the same as this. Okay, and then from symmetry, you see this is 0, and if it is 0, it remains 0 whatever you do. Okay, so it turns out that this symmetry simply means that this double limit is 0 for any beta. But these are different from this. I mean, some people say that physicists do not care about the order of limits, but sometimes we must. And in this case, if we take the limit in this order, we see this non-trivial behavior. If you do it in this way, you don't see anything. Okay, but anyway, there's something very subtle going on. So when you have non-zero spontaneous magnetization in this region, this subtlety means, I mean, you can, in this case, you cannot exchange the order of the limits. And in this case, we can say that this global spin flip symmetry, which led to this trivial result, is spontaneously broken. Even if you let h go to 0, this is non-zero. So this is one manifestation of a spontaneous symmetry breaking. Okay, the next question is, can't we characterize this ferromagnetic order in the case of h equals 0? As we have seen here, if h equals 0, this expectation value is 0 for any beta. So you cannot distinguish between low temperature and high temperature regions. But instead of considering this simple expectation value, if you consider this kind of expectation value of 2-point, this is called the 2-point correlation function, the expectation value of the product of two spin variables, then you can distinguish between the high temperature and the low temperature region. In the high temperature region, if you look at this correlation function, then you find that it decays exponentially. Here is a finite quantity called the correlation length, and so it shows this behavior. So it's not quite small when the distance between u and v is less than psi, but if the distance exceeds psi, then it starts decaying quickly and go to 0 rather quickly. Okay, so in this characterizes disordered behavior in high temperature region. And if you're in low temperature region, then this correlation function does not decay, and it tends to a finite non-zero value, which is the spontaneous magnetization squared. Okay, so what does this mean? Well, so here is a possible configuration of spins at site u and v. So there are 4 possibilities, and because of this global spin flip symmetry, this and this must have the same probability, and this and this must have the same probability. Oh, these are the probability that you see these configurations. And if you find that this expectation value or correlation function is strictly positive, it means that these probabilities are strictly larger than these probabilities. What does this mean? Well, this means that two spins at faraway sites, u and v, tend to point in the same direction. They want to do this rather than this. Okay, so this means that they are ordered. They are talking to each other, even though they are far away apart. So this is a manifestation of a long-range order. Okay, so you can clearly distinguish. Okay, and here is a rigorous theorem. So first of all, let me recall that this is a rigorous result, and this is a characterization of beta c. And here is another rigorous result, which characterizes the system in terms of long-range order. So first of all, I take the infinite volume limit, and the limit, you can prove that the limit exists. And actually here, this is a very subtle thing and you can ignore. But here, in order to take L, the limit in which L goes to infinity, I think it's better to define our lattice in this way, from minus L over 2 to L over 2. Anyway, you don't have to worry too much about this. But anyway, so you first take this infinite volume limit, and then for high temperature, in the high temperature phase with the same beta c, you see that there is a finite psi, and this correlation function satisfies this inequality. So it shows exponential decay, and in the low temperature region, people can prove that this tends to, in this limit, this correlation function tends to ms beta squared, which is strictly positive. Okay, so to summarize, we have seen that the ferromagnetic order in the Ising model in dimensions 2 or higher and in low temperatures can be characterized either by a spontaneous symmetry breaking, which is this. So this is the spontaneous magnetization. So non-zero spontaneous magnetization, or by a long-range order, in which case we look at the correlation function at zero magnetic field. And if it does not decay, we see that there is a long-range order. Okay, so this is what we know about the Ising model. All right, now we focus on the XY model, which is our main subject. So this is a definition. I hope you remember. This is our spin, and this is Hamiltonian. Okay, so let me start from with an important theorem called the Hohenberg-Mermin-Wagner theorem. This is a statement, and it applies to models in dimensions 1 or 2 and at any temperature. And it says that this limited double limit is 0. What is this? Well, here you have magnetization spin in x direction, and you sum over. So this is a total magnetization in the x direction. You divide by the number of sides. So this is the magnetization density in the x direction. You take the limit where L goes to infinity, the infinite volume limit, and then you let H go to 0. So this is nothing but the spontaneous magnetization. So this theorem says that spontaneous magnetization is vanishing at any temperature. And this is not surprising for dimension 1, because this was also the case for the Ising model. But in this case, even in 2 dimensions, we see that there's no spontaneous magnetization. So there's no spontaneous symmetry breaking. And we have to say that this is an essential consequence of the continuous symmetry in case of d equal 2. Okay, and we're going to prove this important theorem in part 4. But our proof is different than the original proof, and we make use of the Maclaurin-Spencer argument. Okay, so this is one important thing, and this is an easy thing. So if you go to high temperatures, things are rather normal. So in any dimension, if you are at sufficiently high temperature that this is valid, so beta is the inverse temperature, it should be smaller than this thing. And then this is a 2-point correlation function at 0 magnetic field, at vanishing magnetic field. And this correlation function, it's always positive, non-negative, and it's less than this. What is this? Well, you don't have to care about this prefactor. What is important is here. Since beta is less than this thing, this constant here is strictly less than 1. So this inequality, this factor, decays exponentially as this distance gets large. So this shows that this 2-point correlation function exhibits exponential decay. Okay, so this is quite universal phenomenon, and it applies to many different spin systems, and the proof is not very difficult. So I could have skipped this proof, but for completeness, I include the proof of this theorem in part 5. Well, it's also interesting. Okay, so now let me discuss an approximate result, which is called the harmonic approximation, which is, of course, not rigorous. It's called approximation, and it's due to Franz Wegener. Okay, and we are going to discuss this approximation rather carefully in part 3. It will be a long part. Okay, and this approximation supposes that we are at very low temperature. Okay, beta is very large, and if you do some hand waving assumptions, and if you do some computation, what the result you get is this. First of all, in dimension 1, you see that this two-point correlation function always decays exponentially. This is consistent with what we believe, and actually this is also reverse. And at high temperature, in dimensions 3 or higher, you see that at very low temperature, this does not decay. Okay, so for d equal 1, we see there's no ferromagnetic order at non-zero temperature, and at d equal 3, we have long-range order at sufficiently low temperature. But what is this? In dimension 2, if you do this approximation, what you find, actually what Franz Wegener found in 1967, was that this decays like this. So it's not an exponential decay, it's a very slow decay, which is usually called a power law decay. Very slow decay. And so, and this, well, if you're familiar with critical phenomena, and then you know that at the critical point, sometimes two-point correlation function exhibits power law decay. But in this case, we are at sufficiently low temperature. So at any sufficiently low temperature, this approximation suggests that this two-point correlation function decays with a power law. So this is very exotic. So this suggests that there is a very exotic phase realized only in 2 dimensions. And actually, it is now believed to be true and partially proved. So this is called the Kosterlitz-Thouless transition. And now it is believed that there is a transition point in the XY model in dimension. And if you're above the critical point, then the correlation function decays exponentially. And if you're below the critical point, then transition point, then correlation function decays with power law. Okay, and this power depends on the temperature. Okay, so this is very interesting. This is a very interesting phase transition where the low temperature phase exhibits no spontaneous symmetry breaking or no long-range order, but still there is a phase transition. Let me briefly discuss early essential works on this transition. So as I said, in 1967, Franz Wegener invented this harmonic approximation and discovered that there should be an exotic low temperature phase. And I learned that this work was a part of his PhD thesis. Okay, and then in 1971, Berezinski, he didn't know about Wegener's work, and he rediscovered harmonic approximation and also gave further discussion about the transition. And in 1972, Kosterlitz and Thouless came up with a complete picture of this transition. Okay, so usually this transition was called KT transition, the Kosterlitz-Thouless transition, but recently people started recognizing the contribution by Berezinski, and now many people call it the BKT transition. But it looks like still this Wegener's important work is sort of forgotten, and so I'm happy with this KT. But if you want to add something, I think it's also reasonable to call it the WBKT transition. Okay, Professor Wegener himself is very well known, and he's known for his beautiful works on like renormalization group or the Anderson localization, or he in a sense invented the lattice gauge theory. So he is a very famous theoretical physicist. Okay, so all right. Anyway, this is Professor Wegener, and this is Berezinski, and this is Professor Kosterlitz, and this is Professor Thouless. So as you see, they got Nobel Prize in 2016, and Professor Kosterlitz got this prize mainly for this transition, the discovery of this transition, and Professor Thouless did more. So actually he receives 1/2 of the prize, and so he did so many things. But one more things, the other thing related to this Nobel Prize is that he sort of initiated the very important field of topological condensed matter physics by introducing something called the TKNN integer. It's one of the topological indices to understand quantum Hall effect. Okay, so it's a very important work, and I want to mention that this K of TKNN is Mahito Komoto, who is my very good friend. So I want to mention this. And of course, Komoto made a very important contribution to the subject of this Nobel Prize. Okay, so the other person is Professor Duncan Haldane, and he did not basically contribute to the discovery of this transition, but he has done so many beautiful works related to, again, topological condensed matter physics. And one of his contribution is about quantum spin chains. And I want to say that I did some works related to what Professor Haldane did. So I still don't have any mini courses in this series, but if you look at my YouTube channel, you will find some lecture videos related to what Professor Haldane did. All right, so that was a brief history, and let me go back to physics again. So we have found that there was an indication that in dimension 2, the XY model exhibits a very exotic phase transition. Is it true? Yes. So here are rigorous results. First of all, this is an upper bound, and it's called Macmillan-Spencer theorem. And this is, as I said, this is our main topic of this mini course. Okay. So what does this theorem say? Well, it says that in dimension, and if your magnetic field is vanishing, and then for any bit, for any temperature, you have an upper bound for this correlation function that decays with a power law. Okay, and you can also control this power at very low temperature. Okay, so this shows that at any temperature this decays, and so this establishes that there's no long range order. And rather interestingly, this has a power law behavior. Okay, what about the lower bound? Well, it was also done by Frelich and Spencer. This is so the same Spencer, and Frelich, Spencer, they are sort of real big names in the field of mathematical physics or rigorous statistical physics, and they did so many things, and they proved so many important theorems in this field, and most of them are very difficult. And also this one is very, very difficult. It's a very difficult paper, so it's just impossible to discuss their proof in this kind of mini course. Okay, so anyway, they proved the corresponding lower bound at a sufficiently low temperature. Okay, so this rigorously establishes that there is a transition with exotic power law decaying phase at low temperature. Okay, so this establishes the existence of KT transition or BKT transition or WBKT transition, whatever you prefer to call it. Okay, right. So so as I said, there's no way of discussing this, but we shall discuss the proof of this theorem carefully. And so now we have done with 2 dimensions. What about other dimensions? So first of all, in 1 dimension, everything is simple, and if your magnetic field is vanishing and the correlation function decays always exponentially. I think you can prove this in many ways, but you can prove this by using Macmillan-Spencer argument. So if you are interested in, just try after watching my video about this theorem 3. Okay, and this is another theorem this theorem is about dimensions 3 or higher. And then in this case, at sufficiently large beta, it has been proved that a 2-point correlation function at vanishing magnetic field does not decay. So there's long range order, and also this is spontaneous magnetization. Yes, it was also proved that the spontaneous magnetization is non-vanishing. Okay, and this long-range order part was proved again by Frelich, Spencer, and Simon, another god. So, and this is a very interesting paper which uses the method called reflection positivity. And the notion of reflection positivity comes from field theory, quantum field theory, but they discovered that it can be used for condensed matter physics. And there are many interesting applications by these people or by Professor Lieb, who is also another god in this field. Okay, and as for this part, it was proved by Professor Griffith long time ago, and he proved a general theorem that says that whenever you have long-range order, you also have spontaneous symmetry breaking. Okay, so anyway, this is known. So in 3 dimensions, everything is sort of standard, and we have ferromagnetic order at low temperatures. Okay, so dimension 2 is very, very special, and very, in a sense, it's very interesting. So here is another short story about dimensions between 1 and 2. So you can think about some fractal lattices which have this kind of non-integral dimensions. So, and if you apply this harmonic approximation to the XY model defined on this kind of fractal lattice, and then the approximation suggests that there is an interesting low temperature phase in which the 2-point correlation functions decays like this. This looks like the exponential decay, but no, this is the exponential decay in exponential decay, and here you have extra power. So for example, if this is 1.5, and then here you have 0.5. So this is usually called a stretched exponential decay, and it's slower than usual exponential decay. So this result from the harmonic approximation suggests that there is another exotic phase transition in this xy model defined on the fractal lattice. But actually, it was not the case. Unlike in 2 dimensions, the harmonic approximation fails in this kind of case. And Toru Koma and myself, this was an easy short paper, but in this paper we proved that if this fractal dimension is strictly less than 2, then at any temperature, the 2-point correlation function decays exponentially. Here, this is you cannot use usual Euclidean distance here, so we use graph theoretic distance. It's the length of the shortest path that connects 2 points. Okay, but anyway, this shows that there's no phase transition in this case. Okay, so well, this was just a short remark. And before closing this lecture, I want to mention one thing about the Heisenberg model. So as we said, so this is the Heisenberg model, I hope you remember. And we do not discuss this very important model, but let me say what is known. So in dimension 1, there's no phase transition, and you always have exponential decay. Okay, and in dimension 3 or higher, then there is a phase transition, and we know that there is long-range order and spontaneous symmetry breaking at sufficiently low temperature. Again, this is proved by Frelick, Simon, Spencer, and Griffiths. Okay, the same theorems apply. Okay. So these are good. So dimension 1, nothing. In dimension 3 or higher, you have ferromagnetic transition. What happens in 2 dimensions? Okay, there's another very interesting thing. And this is still an open conjecture due to Polyakov. And the conjecture says that in dimension, and if magnetic field is vanishing, then at any temperature, the 2-point correlation functions decays exponentially. Okay. Of course, this is finite correlation length. And this has been conjectured for a long, long time. And I know many people who try to solve this, to prove this conjecture, but nobody succeeded. And well, sometimes people ask if this is really true. So, this is still a conjecture and we don't know. So it has been, this is a model. This is a very simple model with a long history, but this is still a big open problem. Okay, so this is the final slide. So this is a plan for this mini course. So this is part 1. So it was a long part 1, but I discussed background and main result that we want to prove. And in part 2, this is very, very short. This is very, very short. I will just define the model and rewrite it by using angles. And this part 3, will be long, and part 4, these are the main topics of this mini course. And finally, in part 5, I will do some stochastic geometric representation and to prove the exponential decay of correlations. Okay, so thank you very much for watching. That's all for part 1.